Good evening, everybody. Today we are going to discuss internal voltage control of inverters. Before going to that, the last class, a few students asked some doubts regarding this voltage across capacitor and voltage across inductor. How you are drawing these two waves? So very simple. So first of all, you please draw this voltage across this output. So you already know for any inverter, for any load, always it is a square wave only. And here we are discussing with the leading power factor. When we are discussing leading power factor, what happens? The phi angle will be there. That will be in leading nature, right? So what is the phi angle? Already last class I have shown you 45 degrees. That means this angle is 45 degrees exactly. So because of leading, first the current is zero, and later your voltage is going to be zero. That is the first thing. And coming to uh, here, the because of this phi, you are getting this sinusoidal. You are getting some waveform. But why you are getting sinusoidal? I already told you that you please refer class A commutation RLC load. There I have discussed clearly with the equation why you are getting sine waveform, right? So here for any for AC circuits, if you see AC circuits, the phase angle difference between current and pure capacitor is 90 degrees. In a pure capacitor, the current leads the voltage by 90 degrees. Whereas coming to inductor, in inductor what happens? The current lags voltage by 90 degrees. So that concept I am implementing here. So first we will see this current and voltage across capacitor. What is the phase difference? Just now I told you 90 degrees, right? See, whenever this is current is maximum means what happens? This is zero. That is the 90 degrees phase shift. Next, of course, you can see here. Again, the current is negative maximum. This is zero. Again here, see the current is zero, but capacitor voltage is maximum. So with a 90 degrees waveform, you have to draw a sinusoidal voltage waveform, right? And similarly, for this current exactly 90 degrees phase shift, right? So for the voltage across inductor, right? See, whenever this is maximum, what happens? This is zero. Whenever this is zero, it is maximum. Again, whenever this is maximum, this will be zero. Then how to draw this voltage across inductor? The phase difference is 90 degrees, right? So, but what happens? The current lags voltage by 90 degrees. So instead of drawing like that, first you please draw the voltage across capacitor, right? With for this you just draw the 90 degrees phase shift, right? So for this just exactly opposite you just draw. So if it is positive means what happens? This is negative. This is negative means what happens? This is positive because the voltage across the angle difference between voltage across capacitor and voltage across inductor is always 180 degrees phase shift. So that's why the zero crossings are same. This is zero, and this point is zero. This point is also zero. But if it is positive means what happens? Definitely it is negative. And coming to this spike, just here a small change in current will be there if you observe closely. Right, that's why you are getting spike. Otherwise, you just draw the sinusoidal voltage wave. Right. So now I have clarified the doubt also. Now we will move into the voltage control of inverters. So these topics already have discussed in the previous class. Now today's topic is internal control of inverter, right? Voltage control. So first of all, what is the main advantage of PWM control is to vary the output voltage, to reduce the lower order harmonics, and filter requirements are low. Right? We will see one by one how your harmonics are going to be reduced. The main disadvantage of PWM control is switching losses are increases if the switching frequencies increases. One more thing is if the switch is SCR, it must possess low turn on and turn off time, and also it requires forced combination. And coming to today's topic, first we will discuss single pulse width modulation technique. Right. So this is single pulse width modulation. See, actually this is the output voltage of single phase full bridge inverter. Right. So this is constant waveform. Right. We are not changing any voltage here. The output voltage magnitude is also fixed. So if you take the fundamental V01 is equal to 4 Vs by root 2 pi into some sign factor will be there, sin and omega t like that. So magnitude is 4 Vs by root 2 pi r fundamental output voltage RMS. So that is fixed. Still, if you want to change that output voltage, how can you change? That is with the help of this pulse width modulation, then we can do it, right? So here single pulse width modulation. What is meant by single pulse width modulation means for the first half cycle you are having only one pulse. So that is single pulse width modulation. Again, for the negative half cycle, we are having only one pulse. So because of for positive half cycle one pulse and negative half cycle only one pulse, so that's why it is called a single pulse width modulation. Generally, we are calling like that, right? So here the pulse width. What is this pulse width? Is 2d by n. What is n? Is nothing but n is the number of pulses per half cycle. So here, how many pulses are there? Only one pulse. Therefore, 2d divided by 1 is equal to 2d. Therefore, see, this is 0, this is pi, this is 2 pi. Exactly whatever the waveform here consisting, the same angles I have taken. And this is exactly pi by 2 middle of the waveform. Therefore, if this total width, how much? 2d, because n is 1 means 2d. Therefore, here what happens? From this point to pi by 2, this width is d. And pi by 2 to this point is width is d. Therefore, total it is d. Now, how to calculate this point means simply this pi by 2 minus this width. From pi by 2 this point, what is the width is d. Therefore, what is this point? We can call it as pi by 2 minus d. In the similar fashion, this point, what happens? This is pi by 2 and this width is d. Therefore, how can I write pi by 2 plus d? Similar manner for the negative half cycle with 3 pi by 2. So this is pi by 2 means exactly 180 degrees phase shift, right? So at this instant, again if you write down, you will get the same angles, 3 pi by 2 minus d and 3 pi by 2 plus d. Now for this waveform, if you want to find out RMS output voltage, right? So what happens? Vrms square is equal to pi by 2 minus d, this limit, pi by 2 minus d, to pi by 2 plus d, this limit, pi by 2 plus d, Vs square d omega t. Here I have kept here square. Okay. So if you simplify, finally what you will get? V naught RMS is equal to Vs into square root of 2d by pi. Right. So for this square waveform, what is the voltage magnitude? What is the RMS? We already discussed for full bridge inverter. RMS output voltage is V naught is equal to Vs. But coming to the fundamental component is 4 Vs by some root 2 into pi. Now here, what is the output voltage of RMS is Vs into square root of 2d by pi. So definitely we are changing the output voltage, right? That is the first point what I have discussed here, to vary the output voltage, right? So that is I am discussing. Next, to find out the harmonics here. So I am using only Bn component because see, single phase half bridge inverter we have seen, full bridge inverter also we have seen. For every time A0, An values are 0, only Bn value is presented because this waveform is a odd symmetry, right? That means f of theta is equal to minus of f of theta. Then it is nothing but odd symmetry. For odd symmetry waveform, you are getting Bn values. Now this is harmonic analysis of PWM inverter. You know this equation: V0 is equal to A0 plus sigma n is equal to 1, 2, 3 and so on infinity an cos n omega t plus bn sin n omega t. Of course, I said this an, a0 are absent because of odd symmetry. Then directly we are going to find out bn. See, if you want to find out an, a0 values, you can find out by using previous videos. You can see even if you solve it, you will get the 0. So bn, what is bn? 2 by t integral 0 to t b of t into sin omega t d omega. So what is the time period? For every time I will told you that to calculate harmonic analysis, always you have to take the full cycle. So that's why the time period is 2 pi and the limits. The first pulse limits are, see, pi by 2 minus d to pi by 2 plus d. This is the first pulse. Second pulse is 3 pi by 2 minus d to 3 pi by 2 plus d. For the first pulse, what is the magnitude is Vs. Second one, what is the magnitude is minus Vs. Here I didn't represent just because of negative. This is minus Vs. Right. I have written here. So first one is pi by 2 minus d to pi by 2 plus d. Vs sin omega t d omega t plus 3 pi by 2 minus d to 3 pi by 2 plus d minus Vs sin omega t d omega t. Right. So if you cancel these two and take this Vs as common, therefore Vs by pi. So integral of sine means what happens? Minus cos n omega t pi n, and the limits can substitute. And later again Vs by n you can take common, right, outside. So then minus of cos n, first limits pi by 2 plus d, minus of minus plus cos n of pi by 2 minus d, plus cos of n into upper limit 3 pi by 2 plus d minus cos of n into 3 pi by 2 minus t. Right. If we simplify, and finally what you will get is this one. Bn is equal to 4vs by n pi sine n pi by 2 into sine nd. For n is equal to 1, 3, 5. Right. For example, if you take n is equal to even values, let us look at this one, even values. Sine 2 pi by 2 means what happens? It is 0. So here sine 3n pi, 3 into n you can take 2. So sine what happens? 6 pi by 2, that means sine 3 pi, which is nothing but 0. So for even values, always you will get Bn value is 0. So even if you refer the previous videos, single phase full bridge inverter, half bridge inverter, for even values, the Bn value is 0. But here what happens is for odd values, 4Vs by n pi, sine n pi by 2, sine nd. Let us substitute n is equal to 1. Sine pi by 2, how much? 1. Minus sine of 3 into n. N is how much? 1. Sine 3 pi by 2 value is minus 1. Minus of minus plus. So 1 plus 1 is 2. 2 multiplied by 2 here, 4. 4 Vs by n pi, sine n pi by 2, sine nd. Right. See this n pi by 2, every time even if you keep 1 means sine n pi by 2 is 1. I mean sine pi by 2 is 1. If you keep 3, what happens? Sine 3 pi by 2, that is minus 1. So, but while you are calculating this harmonics, you are concentrating on magnitude, but not the sign. So here, so if you substitute this Bn value here, and finally you will get n is equal to 135 and so on infinity, right? Because here this is valid only for n is equal to 135, but not 2, 3, 4 like that. So that's why I kept n is equal to 135 and so on infinity 4Vs by n pi sine n pi by 2 sine nd into sine n omega t. This is in the form of Bm sin omega t. So this total magnitude I'm considering as a Bm, right? So what is V01 peak, right? Which is nothing but substitute n is equal to 1 here. That means 4Vs by pi, right? Sine pi by 2, how much? 1 into sine nd. N you can keep it is 1. Therefore, what happens? Sine t. Therefore, if you go for V01 RMS, what happens? 4Vs by root 2 pi into sine t, right? Now, the second point here, the first one already completed, to reduce the lower order harmonics, right? That part we will discuss now. Now, by using this pulse width modulation, which harmonic you are making to 0? So by using this single pulse width modulation, you are going to make some required harmonic component is 0. That may be 3, that may be 5, that may be 7. Whatever you want to make your harmonic component, make it 0, then that you can fulfill here. So let us go for to make the required harmonic magnitude as 0. Then this sine nd is equal to 0. That means this part sine nd, right, is equal to 0. Therefore, what is nd? Sine inverse of 0. Nd is equal to sine inverse of 0 means what happens? Pi. Therefore, d is equal to pi by n. 2d is equal to 2 pi by n. Why I am returning here 2d means our pulse here width is always 2d. So that's why even we are getting here d. So we are making it to 2d, that is equal to 2 pi by n. Therefore, to make the third harmonic magnitude as 0, then n is equal to t. N is equal to 3. That means if you substitute n is equal to 3, then you can make third harmonic will be 0. Then what is this? 2d is equal to n value is 3. Substitute here 2 pi by 3. Therefore, what is the pulse width? Is equal to 120 degrees. That means if you want to make the third harmonic as 0, what is the pulse width is? 120. For example, if you want to make fifth harmonic 0 means this 2d is equal to 2 pi by 5. So that is nothing but 72 degrees. Understand what I'm saying? Right. So next one, we'll solve one problem, then you will get some idea. So the consider Vs is equal to 100 volts, pulse width 2d is equal to 120 degrees, and find the values of RMS output voltage, fundamental component of output voltage, and harmonic factor for 5 and 7 harmonics, and THD for the full bridge inverter. Right. What is VRMS formula? Vs into square root of 2d by pi. Therefore, V0 RMS is equal to 100 into what is 2d? pulse width is 120. Substitute here, divided by pi. See, this is in degrees and this is in some radians, so some conversion is required. So that's why pi by 180. And finally, what you will get? V naught RMS is equal to 81.60. What is the voltage we have given? 100. What is the voltage we are getting? 81.60. In case of pure square wave, then what the voltage we are getting is some 4 Vs by root 2 pi. So some around you will get some 90, right? But what is here? We are getting 81.60. So that means whenever I want to reduce the voltage, then by using this pulse width modulation technique, right? Then I will change the output voltage. Next, what is the next one is fundamental component of output voltage. So I'm finding only the peak value. If you want RMS, make it root divided by root. What is V01 peak? Just now we have discussed. What is V01 peak? Is 4 Vs by pi into sine d. So 4 into what is Vs value? 100 divided by pi sine d. See, 2d is equal to 120 degrees means d is nothing but 60 degrees. If we substitute, what is the fundamental value? 110.311 p. Right. So from this also you can say, see, V01 peak earlier 4 Vs by root 2 pi, right? For pure square waveform, what is Vrms is equal to Vs in case of full bridge inverter. Vrms is equal to Vs at that time. So V naught RMS is equal to 100 there. Here 81 points. What about the fundamental component? There, if we discussed earlier, is some 90 point something we are getting, but here what happens? 110.311 volts we are getting. This is the fundamental component. And what is this V03 peak value? Right, V03 peak means what is this harmonic? We have to substitute this equation. So this equation you please use it. So 4 Vs by n pi sine n pi by 2 sine nd. In this, what is n value? 3. Therefore 4 Vs by 3 pi sine 3 pi by 2 sine nd. Right. So wherever n is there, you can keep n value is equal to 3. Right. So there I have substituted 3. Forget about this sine 3 pi by 2. That is -1. Always just consider magnitude. And if you simplify, what happens? So 4 into Vs is 100 divided by 3 pi sine 3 pi by 2 into sine 3 into d. Sine 3 into d means 60. So sine 3 into 60 means simply sine 180. Sine 180 is 0. That means the third harmonic is 0. Actually, every time if you see the full bridge inverter or half bridge inverter, the third harmonic percentage is 33.3%. But here we are making that as 0 simply. Similarly, for fifth harmonic, same, in place of 3 you can substitute here 5 and you will get 22.06. Now for this, what is the harmonic factor? V05 divided by V01. So to do it, and finally what you will get? 20%. Right. And next, this, what is V07? In the similar fashion, whatever we have finding here, V05, you will go for V07 also, you will get 15.75. And what is the harmonic factor? Again 14.28. Right. So please remember, this is 20%, this is 14.28. In the simulation we will see clearly. Next, what is THD formula? Vrms square minus V01 square divided by V01 square. So when you are finding THD, you should remove this fundamental, because the fundamental is a useful component. Rest of that 3, 5, 7, 9, whatever the harmonic is, those will consisting of harmonics. So you can use that one. So that's why when you are finding THD, you should neglect. I mean, you should remove. You should make the difference V01 square, right? So what is Vrms square? 81.60 square. What is V01 square? V01 square we are getting this one. Because of RMS, I am making by root 2. So 110.311 whole square divided by root 2. Like this. So, and finally, what is the percentage? 30.6%. So here what is our conclusion is, just now I discussed is, to make the third harmonic magnitude of 0, what is the n value? 3. And what is the pulse width? 120 degrees. Now, see, by substituting this, pulse width is equal to 2d equal to 120 degrees or d is equal to 60 degrees. The third harmonic component magnitude is 0. That is very important point you have to observe. Right. Now, if you go for simulation point of view, so This is the simulation diagram. So here I'm using single phase bridge inverter, right? So this is a pulse width modulation, single pulse width modulation, pulse generation. I will show you pulse generation, everything, each and everything, right? First, we will see the harmonic and fundamental components, all those things. So then one by one, we will discuss whatever we have done in the problem. So that we will discuss clearly. Okay. So now here, this is the output of single pulse width modulation. So in that, here, if you observe, what is V01? So what is V01, right? So this is the harmonic content V01. What is V01? We are getting 110.3 peak. Just now we have discussed, right? What is the total harmonic? Some 30 point, right? Almost same. What is the fifth harmonic percentage? 20 percentage. See 19.96. What is the seventh harmonic percentage? Is 14.28. See here 14.31. Right. So here the third harmonic, if you observe, what is the third harmonic? If you see, third harmonic is this one 0, 0.06. That means almost it is reached to 0, right? So if you want to observe in what in past, right? So that I want to show you clearly. Right? So see here. Here what happens if you want to reduce this frequency, it is better, right? So if you reduce the frequency, you can get clarity. So now see, this is one second. Yeah. So this is fundamental, right? 50 hertz. What about this 150 hertz, right? 150 hertz, that is third harmonic. The third harmonic is almost 0. But again, what you are having, fifth harmonic. See, this is X is nothing but what happens 250. That is fifth harmonic. But what I see, this one is, it will not show, right? So what happens? This is third harmonic. This is 50, 100, 150. The third harmonic is completely 0. Understand what I'm saying? So come back to again this one. What is the RMS output voltage we have to get? 81.26. See, this is almost equivalent to 81.6. This is almost equivalent to 81.6. This is the RMS output. Fundamentally is 110 that I have shown just now. And coming to the pulse generation, so here at a time S1, S2 are turned on. Again S3 and next half cycle S3, S4 are turned on. So these are the pulses, right? One second. So these are the pulses. So see, this is 0, this is 0.02, right? So this is 0.01. So that means this is 180 degrees, this is 360 degrees. For the first half cycle, this is the pulse. For the second half cycle, this is the pulse. And how I am generating the pulses? By taking one triangular wave, which is called as carrier wave, and one constant wave I have taken, and finally I am getting the pulse. Right. So how to get this constant magnitude? I have substituted here. I have given here some 0.333, right? Like around some 0.33. Why I am substituting 0.333, right? So if you go to the previous videos which I have discussed, single phase full bridge inverter, third harmonic percentage how much? 33.3 divided by 100. Please substitute here, and you will get 0.33. For example, let us say, for example, right? For example, if you want to eliminate fifth harmonic, fifth harmonic means what happens? You have to use 0.2. Why? Because 1 by 5 how much? 20 percentage. 20 percentage means what happens here? I have to use some 0.2, right? So, and if you run the simulation now, the fifth harmonic will goes to 0. So if you run the simulation clearly, and just 1 second, the simulation is running. I will show. So just wait. So the 50 analysis. So in this, to go for the list, yeah. What is the fifth harmonic now? 0%. See, the fifth harmonic is 0%. Understand what I am saying? And here what happens? The third harmonic is raised here. Earlier what happens? Third harmonic 0, fifth harmonic is 20%. Now the third harmonic is 20%, but what about the fifth harmonic? 0. Right. So now the PhD is changed slightly, and fundamental magnitude also changes. The fundamental magnitude also changes. If you remove this, what happens is fifth harmonic you are making to 0, right? So this is about your single pulse width modulation. And coming to here, this frequency is always 50 hertz frequency. You have to use it because here the pulses will be generating only on the 50 hertz frequency. For that, I have used the 50 hertz frequency only. So this is about your single pulse width modulation, right? In the next class, we will discuss the multiple pulse width modulation, right? So here the multiple pulse width modulation means what happens simply is nothing but it consisting of 2 pulses per half cycle or 3 pulses or 4 pulses like that, right? And the same procedure, harmonic analysis, and again you have to go for calculation part and everything. So in this class today, I clearly shown the where the output voltage I have clearly shown, right? And to reduce the lower order harmonics, now we have seen third harmonic I have make it 0 and fifth harmonic also I make it 0. And filter requirements are low. See, actually, for full bridge inverter, if you observe what is the THD is 48 point something. Now what is the THD in this class we have discussed, that is some around some 30 points. So once this harmonics are reduced or lower harmonics are going to be 0, the filter arrangement, the filter requirements is going to be reduced, right? So in the next class, we will go for the multiple pulse width modulation, later sinusoidal pulse width modulation. Thank you.